Before we move to the third classification of the turbine, let's define few important terms. What is the head of the turbine? Head is basically is the height difference between where the water enters into the hydraulic system and where water leaves the hydraulic system. We measure it in meters. So there are two types of head which are important. The first is gross head. So as we can see in the diagram, the gross head is the difference between the headrest level and tail rest level whenever there is no water is flowing in the system. So gross head is the difference between the headrest and tail rest. Second type of head is net head. So whenever water flows through the penstock, there are various types of losses which occur in the flowing fluid. We have discussed these types of losses in the previous chapters, namely frictional losses which occur due to friction. So we consider frictional losses which are responsible for loss of head in the turbine. So to calculate net head, we subtract the head loss due to friction in the pipe from the gross head. So if we denote gross head of the turbine by Hg and the frictional head loss by the term Hf, so the net head will be the difference of gross head and head loss due to friction. As we already studied in the flow through the pipes, the head loss due to friction is generally calculated with the help of Darcy-Weisbach formula, which is written there in this presentation. So Hf we calculate as 4F into V square upon D into 2G, where V is the velocity of the fluid in the penstock, L is the length of the penstock, D is the diameter of the penstock, and G is the acceleration due to gravity. So depending upon the head of the turbine, we classify the turbines into high head turbine, medium head turbine and low head turbines. So high head turbines, the available head is above 150 meters and between or less than 2000 meters. So Pelton turbine is a high head turbine. In medium head turbine, the available head is between 30 meter and 130 meter. So Francis turbine comes into this category, which is a medium head turbine. The third one is low head turbine, in which the available water head is below 30 meter from the axis of the turbine. So generally low head turbines are high discharge rate turbines. So Kaplan and propeller turbines are low head turbines. High head turbines have low discharge rate. So Pelton turbines are high head turbines and their discharge rate is low. Francis turbines are medium head turbines and their discharge rate is also medium. Before going to the next classification of the turbine, we define some important term related to the hydraulic turbine, which is specific speed of the turbine. So specific speed is the speed of the turbine at which a turbine runs under unit power and under unit head. This is the most important characteristics of the turbine. So we calculate the specific speed of the turbine with the given formula, where Ns is equal to the specific speed of the turbine, n is the speed of the turbine, p is the power of the turbine, h is the head of the turbine. So specific speed can be calculated with the help of the formula ns is equal to n root p upon h raised to the power 5 by 4. So depending upon the specific speed of the turbines are classified into low specific speed turbines, medium specific speed turbines, and high specific speed turbines. In the low specific speed turbines, the specific speed of the turbine is less than 50. Pelton turbine is an example of low speed turbine. In the medium specific speed turbine, the specific speed lies between 50 and 150. So Francis turbine is a medium specific speed turbine. In the high specific speed turbine, the specific speed of the turbine generally lies about 250. So in this category, Kaplan and propeller turbines are considered. Now we will discuss the important difference between impulse turbine and reaction turbine. As we have already defined in the classification of the turbine, impulse turbine, the available energy is only kinetic energy. So all the potential energy of the water is converted into the kinetic energy with the help of the nozzle, and the nozzle is fitted at the end of the penstock. So available energy is kinetic energy in the impulse turbine. In the reaction turbine, both type of energy is present, kinetic energy and pressure energy. Only a certain portion of the pressure energy is converted into the kinetic energy of the water. So both type of energies are present at the inlet of the turbine. In the impulse turbine, we regulate the flow of the water with the help of the nozzle without any loss. So in the reaction turbine, flow is regulated, but there are losses due to conversion of pressure energy into kinetic energy. There are certain losses. So impulse turbine is installed above the tail race, and reaction turbine is generally submerged in the water below tail race. In the impulse turbine, blades are active only whenever they are in the front of the nozzle. They should be in front of the nozzle so that the water strike on the surface of the blades properly. Otherwise, there will be bad effects on the efficiency of the turbine. Efficiency of the turbine will go down. In the reaction turbine, the blades are active all time in all positions. These are the important differences between impulse and reaction turbines. Now we will discuss the few important turbines: Francis turbine, Pelton turbine, Kaplan turbine, one by one. So first we will discuss Pelton turbine. In the presentation, the diagram of the Pelton turbine is shown. As we already discussed that Pelton turbine is a high head turbine, it is a tangential flow turbine, it is an impulse turbine, and the shaft is horizontal in Pelton turbine. The Pelton turbine is named after L.A. Pelton, an American engineer. So in Pelton turbine, water strikes the bucket or blades of the rotor in a tangential direction. It is a high head turbine and head varies from 50 meter to 1300 meter. It is a low specific speed turbine and the specific speed varies from 8.5 to 30 in case of a single jet, or in case of multiple jets, that is 2 or more than 2 jets, the specific speed varies between 30 and 51. The main components of the turbine are nozzle and spear, runner and bucket, casing and braking jet. It is the diagram of the Pelton turbine. We can see a branch pipe. At the end of the branch pipe, a nozzle is fitted. We can see the buckets attached to the runner or rotor of the turbine and a casing of the turbine. So as we can see in this diagram, this is a large diameter pipe which we call penstock. At the end of this large diameter pipe, a nozzle is fitted, and nozzle increases kinetic energy of the flowing water. So in needle type of attachment, we call it spear. This spear is used to regulate the flow of the water in the turbine. Whenever this spear is pushed backward, the supply of the water increases and more water enters in the turbine, more water striking the rotor of the turbine, and more force generated and more power is produced by the turbine. This is the casing of the turbine, which is used to avoid splashing of the flowing water. So this is the rotor of the rotor of the turbine. The vanes, these are the guide vanes or blades or buckets of the turbine, which are fitted or attached on the rotor of the turbine. So whenever water flows through the nozzle, pressure energy is converted into the kinetic energy. This high velocity water strikes on the surface of the blades of the rotor due to change of the momentum of the flowing fluid. The force is exerted on the blades of the rotor. This force rotates the rotor of the turbine, and the shaft of the turbine is coupled to the shaft of the electric generator. So rotating shaft of the turbine rotates the electric generator, and electricity is produced in the electric generator. The runner of the Pelton turbine is a circular disc, and the buckets are fixed on the periphery of this circular wheel. The shape of the bucket is double hemispherical cup type. In each bucket we have a splitter. The work of the splitter is to divide the jet into two parts. The runner of the turbine is made up of cast iron or cast steel, bronze or stainless steel, depending upon type of head required. As we already discussed, the casing is used to prevent the splashing of the water. It also acts as a safeguard, and the casing is made up of cast iron or fabricated steel. Next important component is braking jet. So whenever we stop the supply of the water from the dam, we cut off the supply water to the turbine. So due to inertia force, the rotor of the turbine continuously rotate for some time. So we want to stop this rotor, so we use a braking jet which is installed in the backward, which is installed on the top of the turbine, and the water is supplied which strikes on the back surface of the bucket or runner, which exert a force in the opposite direction of the rotation of the runner. So whenever a opposing force is exerted in the opposite direction of the rotation of the runner stops. So braking jet is used to stop the runner whenever the supply of the fluid or water is cut off. As already told, amount of water striking the bucket of the water is controlled by the spear in the nozzle. When the spear is moved backward, more supply of water can be ensured, more water will be striking the runner of the bucket of the runner. Whenever the spear is moved forward, the supply of the water is decreased. So the shape of the spear is of conical type. It may be hand operated, it may be electrically operated. So we can clearly understood the shape of the bucket and the working of the or movement of the spear as in the shown diagram. As we previously discussed that whenever water is leaving the nozzle, the bucket should be in front of the nozzle so that it can exert the required force. If it is not in front of the nozzle, then the jet will be completely missed out and a lot of energy will be wasted. We will not obtain the required efficiency from the turbine. This is the diagram which is showing that there are 6 nozzles used in the Pelton turbine. So we can notice various things such as this is an attachment for the spear movement, this is the nozzle, this is the rotor, these are the buckets, this is the rotor shaft which will be coupled to the generator shaft. So students, up to here we have discussed about Pelton turbine. Thank you for watching. Thanks for your patience.